All right, so as I was mentioning though before, like we focused on exponential logarithmic functions, and that was kind of a good way for us to jump into some application problems. What I do hope that you see though is some of those application problems are similar to what you saw in college algebra. Okay, so some of that stuff carries over, but we definitely wanted to look at it from the perspective of how does a derivative help us? So like how we were talking about from an exponential standpoint, like if you have dy dx equal to ky, well, hey, the k was the growth rate, the y was the original function you're working with, right? So that was one of the nice things where we can use a differential equation to say, hey, this is still exponential, okay? Now, moving forward, though, we want to make sure to take some of the derivatives from other types of functions and bring it all together for us as far as how do we use these to describe a function, okay? So things that we're going to bring into this, though, is looking at the rate of change and how it tells us when a function's increasing or decreasing. We'll also add in some new terms like concavity, right? I don't think we've really talked about that at all, but we're going to use that to kind of help describe the function's behavior, okay? Now, as far as graphing a function, make sure you remember there's certain things that we definitely want to be comfortable with. Know how to get things like a y-intercept. So don't forget, just plug zero in, find your constant terms. Those are definitely things that you want to be comfortable with. Be careful when you start getting to other types of functions, though, like logarithmic or exponential, with how that zero works out. Okay, so those are some of the things we plugged into the last couple of times we met. Now, the reason I chose this function here is because when we deal with polynomial functions, what do we typically want to do when we go to find our x-intercepts or zeros of a function? All right, so if we set this equal to 0, what do we want to do to this function to solve? Like this graph here is definitely, we need to gather points to try to get a graph out there, okay? Finding intercepts, definitely one of the things we want to have to help graph this. What you'll see here, though, is anytime with polynomials, what we want to do is get into a factored form. So like this particular problem, what we're thinking is, hey, we might have something that looks like this. The only thing that we could be kind of certain about, it's probably going to look like this. And the only reason I'm able to say that is 2 is a prime number. The only factors of 2 are 2 times 1. So my factors are going to have that structure. So the question is, how do we get from there to there, right? So anytime you have 4 factors, remember to try grouping. Grouping is always a good thing to do. I know we haven't done this a lot lately, but just make sure to try. Make sure to watch out for stuff like what we'll see here is that grouping in the end does not work. How do we know grouping doesn't work here when you just do a quick glance? You don't even have to write it out, of course. Make sure you see that these are not the same. There's nothing I can do with this now. Okay. So one of the things that can come up with polynomials that you might remember from college algebra we haven't seen in a while is that, hey, to get to factors, sometimes we have to use synthetic division. Okay. For the most part, synthetic division, I've just used it to evaluate stuff in this class. Just like, hey, this is a nice way to evaluate. Use that here if you wanted to. Plug in 1, plug in 2, plug in 3, to help build a graph. But here, when I go do my synthetic division, I'm going to look at what those possible rational zeros. You might have had a teacher say like the rational zero test or PRZ, something along those lines, possible rational zeros. That every college algebra teacher kind of does this differently, right? But the key is the 2 things you want to look at are your constant term and your leading coefficient. All right, so this little set of values here will come from the factors of your constant term. So plus or minus 1, plus or minus 3, and then those divided by the factors of the leading coefficient. So thankfully here again, it's only 2 and 1. So the only other options we will have is 1/2 or 3/2. Okay. Now, the thing about polynomials is none of these are guaranteed to work. None of these are guaranteed. Hopefully they work though if I'm asking you to graph this, of course. But none of these are guaranteed to work. The one thing I would point out here though is understand that at most 3 of them can work. That's it. because of how polynomials work, right? The degree of this polynomial is a degree of 3. So at most, only 3 of these can work. Okay. With that said, just go through your list, right? Pick a number to start with. So let's start with the 1. Now, as far as synthetic division is concerned, the main focus we took on this was just evaluating stuff, right? I kept using that. So like here, f of 1 equals 0. Hey, that's what I was looking for, was a 0 of the function. So we know that one x-intercept occurs here based on that first synthetic division. Okay. Now, what we really wanted this for, though, was the factoring right now. Since we wanted to find all the zeros of this function, we need to take this from a factoring perspective. Okay. So what we can do now is say one factor is x minus 1. The part that you need to make sure you remember from this is getting the quotient. 2x squared plus x minus 3 is going to give you the rest of the factors that we're looking for. Okay. Definitely not something we've done a lot lately, so I wanted to make sure to review it just in case it comes up. You know, on a test situation, yeah, maybe probably factoring by grouping is a little bit better choice for me, to be kind to y'all, right? If it's a test situation, but it's still definitely something. Don't forget that this is out here, that you might have to do this from time to time. Everyone follow me with that? Now, continuing here, what you'll find is that quadratic that we got from the quotient is actually factorable. So if you factor that quadratic, whatever method you're comfortable with there, you'll get 2x plus 3 and x minus 1. So what we'll see is that, hey, we have x equal to 1 from 2 factors. That's called multiplicity, though, and we'll talk about that in a second when I go graph it, because it occurs twice. This second factor, is going to be negative 3 halves. So we actually now have another point that we can plug in to our graph. Right about here. Now, like I said, I know it's been a little while probably since you've seen the synthetic division approach to that. I just want to make sure to review it in case it comes up on the homework. Try grouping first, of course, so that's much more straightforward. Okay. Oftentimes though, when you're building models of functions, you're going to be dependent upon software to help you find these quote unquote zeros. Okay, so understand that as well, that, hey, what are some computer programs or softwares that would help us in this process? Will be something that we usually going to look for in that. Okay. With that said, though, do we have enough information to actually graph this, though? Other than plugging in more points, right? Technically, we don't really have a lot of information here. We can go plug in stuff like -1, -2, 2, 3. Plugging in points, though, is a tedious process. Okay. Now, as far as this is concerned, though, from our calculus perspective, we can add a couple things that will help us. The derivatives will definitely help us, and we'll look at that in a second. Okay. But another thing that can help us from a calculus perspective is end behavior. So this is where limits to infinity help us. So limit as x goes to positive infinity of our function, and limit as x goes to negative infinity of our function. Okay, so in behavior is definitely something you should be comfortable with. Let's look at the left hand. Let's look at the right hand. Let's see if it's rising or falling. Okay. Limit notation, though, is the proper way to write that, is what we found. Okay. So as you look at this function, this right here is going to have the most control over the outcome of a limit when it's going to infinity, right? So as x goes to infinity, what is x cubed going to tend to? This is also going to go to infinity, right? Everyone agree with that? So would we agree then that I could say this goes to infinity? What's the difference though with a negative infinity? Specifically, make sure you remember that if you look at like -1 cubed, hey, that is -1, right? So as we go to negative infinity, that term is now going to go to negative infinity. Okay. What we'll find here is that means I can do stuff like this in my graph. So I know that this is going to happen when I look at my graph. Other things that you can take from college algebra, though, is multiplicity of zeros. Okay. So one thing that we can look at here is highlighting the fact that x equal to 1 is a zero that occurred twice. So it has a multiplicity of 2. So if you remember for your x-intercepts there, anytime that occurs, you're going to bounce off the x-axis and then move forward. Okay. Anytime it occurs an odd number of times, we're just going to cross through. It's almost like if I zoomed in on that -3/2, it should be like a straight line going through that x-intercept. Okay. Now from there, though, again, we would have to gather more points, but let's say it just does something like this. All right. Even with, the limit in place, it's not that much more help. However, what occurs here and here that we should be familiar with? When I highlight these points here, what is special about those points when we think about the calculus we've discussed? Horizontal tangents, right? These where we have horizontal tangents occurring. Everyone comfortable with recognizing that? Like what we're going to end up calling turning points of a graph. That's where we're going to find horizontal tangents. Okay. What derivative do we need to find horizontal tangents? That's where our first derivative comes in. Okay. We're going to find our first derivative. And as we just dealt with a lot of this problem here, having to set it equal to 0, guess what? We're going to do the same thing there. Okay. That's why I said, let's find the first and second derivative. Okay. Is there any concerns though with me getting to the y-intercept and x-intercepts here that I cleared for somebody? As I shared with the others, you're not always going to have to use synthetic division to solve this. I just created one to make sure that one of the zeros had a multiplicity of 2. I wanted that to be a little bit nicer that, hey, I can look at this one here and know that that was going to happen just based on this, what we were taught in college algebra. Okay. Are there any concerns with the limits to infinities of my function right now? Getting the end behavior, going to positive infinity or negative infinity here. Are we okay then with my quick sketch here, knowing that I had to turn and all that? All right. Now, what I'm going to do here, though, is continue on with this function. Let's go find our derivatives, and we'll go back to connecting it all together. So remember our function notation, we use f prime of x for the first derivative. What's nice about taking the derivative of a polynomial, though? What derivative rule are we going to use for the most part, right? Use our power rule, right? And make sure to go use through and just each term at an individual time. So this first one is, hey, it's 2 times 3, so that'll give us 6x, and then take 1 away. Minus 2x with only 1 left over. Minus 4. Okay, so make sure you're comfortable with your power rule there. Even better, I said not just the first derivative, but let's find the second derivative, right? So we're going to say, hey, the second derivative of our function is just taking the derivative of that. Get 12x minus 2. Is there any concerns with getting those two derivatives here? Definitely the nicer part of a polynomial, right? Getting derivatives of a polynomial, hey, that's pretty straightforward. I can jump to it, okay? As you saw on the first part, though, setting this first derivative equal to 0 is going to be important for us. All right, this is going to be where we get to what we call critical points. So this right here is going to be getting critical points. The reason we're calling them critical points is those are points at which a horizontal tangent can occur. That doesn't mean there will be a horizontal tangent, okay, but that's where they could occur, sorry. Things that we have to be careful of, like an absolute value function, right? If I think about the absolute value of X, what shape does that have again? If we're looking at this from a graph standpoint, a V shape, right? The function is not differentiable when we have sharp corners, right? So we have to make sure to remember, like, it can't no derivative, right? Not differentiable. Polynomials, though, we're good because they're all smooth terms. Okay, so more often than not, unless it's something else going on, like what we'll see sometimes like this, more often than not, there's going to be a horizontal tangent involved. Okay, everyone follow me with that? Now, setting that one equal to 0, you'll find it's factorable again. It'll be what, x minus 1 times 3x, was it plus 2? Sorry, my brain needs to see this again. Yeah, plus 2. I'll let you do that on your own if you need to see more, but make sure you see what I did here is I factor out a 2 out of all those 3 things that are even. So that's where this 2 is coming from. And then the factors of that trinomial left over are going to be where these are coming from here. Okay. Now, which one do we see repeated? Make sure you see that. As I mentioned, I intentionally wanted multiplicity here. The x minus 1 occurred 2 times, right? So when we go over here to the first derivative, there's confirmation that there was a horizontal tangent at that x-intercept. Okay, I did that on purpose. So this is the one that we didn't see before, but now we have. Okay. Any concerns though with me getting to the first derivative and just setting it equal to 0? Now, understand we will eventually do the second thing with the second derivative. I'm not going to try to spend too much time on that today. But make sure that you see we can definitely do that as well here. If you set that equal to 0, you're going to get 2 over 12, which is 1/6. Okay. I'm going to point it out though, just kind of as we look at this graph in more detail, where that point is on the graph. Okay. Any questions though, as far as getting the derivatives here, just to make sure we're all good? All right, so this next slide here, I got everything summarized on the left side here. So make sure you see I have the function, the first derivative, second derivative. Remember, this was our y-intercept that we found. This is what happens when we set the first derivative equal to 0 to get x-intercepts. I set the first derivative equal to 0. I said that wrong, y'all. I set the function equal to 0 to get x-intercepts. We set the first derivative equal to 0 to get what we're going to call critical points, where horizontal tangents occur. Okay. As far as this graph was concerned, these points we can have confidence with because we've got that from that whole factoring process. We can now improve our graph though using that first derivative. One way that we handle that though is this piece here. As I mentioned, we should be comfortable with that right away because, hey, we learned that that's where we're going to bounce off the x-intercept with a nice smooth turn in college algebra. This point is only confirmed to do that based on this value here when we look at the first derivative, horizontal tangent, okay? So let's go plug the negative 2/3 into our function then. So f of negative 2/3, okay? And this is where I would definitely say, hey, make sure you're comfortable with your calculators. But I'm going to plug this into my function because this is going to help me make my graph a little bit more accurate than it was before, right? I didn't know where the turn occurred, but now I know where it occurs. It occurs at negative 2/3, okay? So this is where I'm going to put that 2x cubed minus x squared minus 4x plus 3. I'm plugging in negative 2/3. And it tells me it's what, 125/27. So we're just gonna do our best to put it -2/3. It's 4.6. So roughly right there. So if we go back to my original sketch, I was nowhere near that technically. Okay, so if you go back to what I did here, I was closer to 4 than I should have been. But now that I can find that point, I can definitely improve my graph. Okay. Now I'm still graphing by hand. I'm not expecting perfection here, but make sure you see that means I'm going to do this and then turn back down and go straight through this next x-intercept. Okay. Now, where does the 1/6 lie in all of this? Or what you're going to find that 1/6 is going to be about right here. Okay. Typically, you're going to find it's pretty close to halfway between our two horizontal tangents. Okay. Not, I'm not saying it's going to be halfway between them, but somewhere in between our horizontal tangents, that's where we're going to see that here. Okay. So this is going to be x equal to 1/6. What you're going to see here, if you look at this side of the graph, it is going to kind of have a downward orientation. On the other side of the graph, it's going to have more of an upward orientation. And when I think about that, think of just like x squared by itself. We think about the graph of x squared. This would be positive x squared. Where if I did negative x squared, it's going to look like this. So that's why I'm using the word upwards or downwards, just kind of based on reflections. But as we go through Friday and next week, we're going to talk about concavity. That's going to be the word that we use to describe that. But just make sure you can see, I kind of compare it back to just the x squared real quick, get that kind of general U shape idea. But that's just one portion of the graph. It's not the entire graph. Okay. Any questions with the points and why I use them to help me with this graph? So the one thing then I would highlight again is, remember, the reason we're using the first derivative is that gives me horizontal tangents to help know where my graph is having that smooth turn because it's a polynomial. Okay. My question for you before we go on the next one, what's going on from this point to this point? What's the function doing? It's decreasing, right? We can get the intervals of decreasing, increasing, and all that now that we know how to find where these critical points occur, right? We can go in now and say, hey, I know my function without even looking at the graph. Okay. We didn't have to do that, but we know our function is decreasing from that -2/3 to 1. The graph helped us here, but we're going to talk about, that'll be another thing we talk about, is how do I just kind of write this out instead of having to graph it all the time. Okay. I wanted to graph it today to make sure we're comfortable with that process, but start building images of what that will look like moving forward. Okay. Any questions, concerns up before that second function? Now, this one's definitely going to be fun. And no, as we go through the next few days, I'll mix in the exponential and logarithmic perspectives as well. I just wanted to make sure to step back and review some of the different things we hadn't focused on because we took, introducing the derivative of those functions first and foremost. Okay. Here, though, we have a rational function, right? Different ways to handle this depending on what you're trying to get to. Okay. Right now, the one thing that is nice to get to is just go ahead and plug in 0 for everything. Get that y-intercept. Okay. What is the y-intercept going to be when you plug in 0 here? Still the constant terms, right? Just happen to have a fraction left over, 19/4. Okay. Well, 19/4 is not the greatest thing to work with, but the nice thing about it, it's pretty close to 5, right? Because 4 goes into 25 times. So I can get a pretty good plot of that one. Not always going to work out nicely, but just do your best. Make sure you're practicing drawing your graphs by hand. I know the software gives you stuff to do the graphs on the computer, but you need to be practicing them by hand as well. With that said, though, there is something we need to talk about here, because as we talk about x-intercepts of a function, we now have a rational function, okay? When I look at a rational function, if I try to set it equal to 0, the denominator is kind of not needed, because you're in the situation of like a over b equals 0. Well, hey, I could just multiply the denominator on both sides and set the numerator equal to 0. Okay. Can the denominator ever be 0 though? No. So what I would encourage you to do anytime you work with a rational function is, hey, let's go right off the bat and state those restrictions. I know we've kind of discussed it, but just as a reminder, don't forget to go state those restrictions too. What you'll find is the denominator is for restrictions, but your numerator is going to help you find those x-intercepts. So when you set the numerator equal to 0, that's going to give you the possible x-intercepts if it has any. But we definitely want to set the denominator equal to 0, because that's going to tell us what number or numbers not to use, if any are restricted, okay? This one here, as far as factoring, is kind of nice. But make sure you see here again, I did that multiplicity, right? X plus 2 squared is another great way to write that. So we'll just say like, hey, x cannot be -2. Can we factor the numerator and what you're going to find there? No, we can't factor. So what do we have to use when we can't factor these? Well, syntax is not going to help us here because we can't factor. You can't factor quadratic. What does that put you into having to use? The quadratic formula or completing the square. Okay, either way. Okay. Now, what you'll see here is just make sure you go back and review the quadratic form if you haven't used it in a while, because I know we don't necessarily use it every day. The one thing you have to be comfortable with the quadratic formula is simplifying it, right? So if we go through here and simplify it, trying to remember what I got. The square root of 5, that's what it. All right, so if you once you simplify that all the way down, make sure you're getting something that looks like -2 plus or minus the square root of 5 over 5, or another way to write that would be -10 plus or minus the square root of 5 all over 5. Okay. I'm gonna write it this way though, because what number did we just state we can't use? -2, right? So this is gonna help us kind of compare it to that -2, okay? But like the square root of 5 over 5, that's a decimal value that we can just approximate real quick. It gives us 0.44, so we'll just kind of use 0.5 as just a quick estimate. So as far as looking at our x-intercepts, roughly right here. Okay. I went to -2, and then a little to the left and a little to the right. That's why I like this form here. Hey, go to -2, go to the right, go to the left, 0.44. Okay. This is what you'll probably naturally get to just doing the quadratic formula, but just see that breaking into two fractions, that's where the -2 comes from. Now, what's going on in between these, right? Well, hey, more than likely, we can't plug in -2 because I can't have 0 in the denominator, right? I could not factor this, which means I definitely know right? One of those things we have to take from college algebra is that there's a asymptote here that I have to be aware of. Okay. Everyone good with the x-intercepts and y-intercepts? Y-intercept, sorry. Are we okay with why I put a vertical line there? Now, I found the x-intercepts first to see if I could factor this. I cannot factor that, so it's not gonna help me moving forward. If it was factorable, there might have been an x plus 2 in there that would have made this easier to work with, okay? So please understand that. The next step then is let's bring in our limits, okay? One of the limits that we definitely want to look at is the limits at the in behavior perspective. So the limit as x goes to positive infinity of g of x, the limit as x goes to negative infinity of g of x, okay? Now, this is going to be a situation though, remember with a rational function, we can look at the leading terms, okay? If you go back to some of the stuff that we talked about, we can divide every one of these by x squared. As long as I divide all of these by x squared. I picked x squared because that's going to get rid of these here. Okay, so that would be the whole focus there is let me get rid of these. So there's no x's on those terms. The 4 that will be remaining will have an x in the denominator. So if x is in the denominator, what does it go to when we go to infinity? So if you have the limit as x goes to infinity of 1 over x, what does that equal? 0. Okay. Well, that means all of these would go to 0 here based on this fact that we've used quite a bit in the course, leaving us with what in front? 5 and 1, right? Well, 5 over 1 is just 5. Does it matter if we use negative infinity? Would that change it? No, right? If you remember, this is where those horizontal asymptotes came from that we've talked about, okay? Now, do you have to go through and do all that work? No, make sure you use observation skills, okay? To me, we've talked about what this is. I've made you do this on a test, right? So if you know you're working the rational function, hey, these are both x squared. So as I go to infinity, both of these will work at the same level, right? So I'll just take their coefficients. Follow me on that? Well, that's exactly what we talked about in college algebra if your teacher had time to get there, okay? Is that, hey, for horizontal asymptote, just look at the degree of the numerator, degree of the denominator. If they're the same, then your horizontal asymptote is just the ratio of the leading coefficients. So that's where I'm going to put this line here for, okay? Now, from a calculus standpoint, make sure you state this, just kind of make a quick statement of it that, hey, this is how we know that that's true. Now, with that said, we have 2 more limits we need to discuss. Oops. Because we have a vertical asymptote here, we need to look at the limit as x approaches -2 from the left of our function. And the limit as x approaches -2 from the right of our function. Okay. Do we have to go do the table for this, y'all? A table is how we would have done this though, right? Does everyone understand that? Table is definitely how we would have done this, but look at these 2 points here. I start up here, it goes here. Where do you think another point would be? Above this or below this? Probably gonna be below it, right? You could plug in numbers if you need to, right? If you feel you need the table to see this, please do that, okay? But what you're gonna find is if you go plug in like -1.9, let's just do it just to show it. Sorry, give me a second. Should have kept them in my calculator, huh? So I did negative 1.99. So if we look at just kind of a quick perspective, G of negative 1.99, I got negative 10,000 basically, rounded to. There's no way I'm even gonna be able to plot that. But the key is that it's negative. What I found is negative. So if I go draw a quick sketch of my graph right now, over here it's gonna approach zero, never get it. But here I know that it's going downwards forever. Okay, so what is that limit approach then? Well, hey, from the right-hand side, that's going to approach negative infinity. Let me shrink this so I have a little bit more room. Okay, so from the right-hand side, it's negative infinity. Well, based on where the x-intercept is on the left-hand side here, do you think it's going to change a lot? No, it almost looks like there's a little bit of symmetry here. Does everyone see that? That just based on my x-intercepts, there might be some symmetry here. If you want to confirm that, go plug in -4. Because what I'm thinking we're going to get for -4 is going to be 19/4. So if I go put it in calculate -4 for my calculator here, guess what I got? I got the 19/4 that I expected. Okay. Now, how would you know that's going to happen? Since I factored that denominator, I got x plus 2 squared, right? Well, we talk about quadratics. There's some symmetry there with quadratics. Well, with rationals, sometimes there's some symmetry around asymptotes too. Not always. It's just the way I made the function. Okay. When we look at the derivative, you're going to see this function is not as bad as it seems. Yes, the derivative is going to be some work involved, but hopefully what you'll see is after we get past the original function to the first derivative, hey, it wasn't as much as it seemed like it was going on the surface. One thing you could do here, if you remember, use your long division. I'm not encouraging you to say do your long division, but that would be something you could do to show that, hey, there might be a way to clean this up a little bit. Okay. But what you'll find here is both of these end up going to negative infinity. That's how we just now confirmed we have a vertical asymptote at x equals -2, but this time the limit actually exists. It just the limit goes to negative infinity. Okay. Now, when you have a vertical asymptote, expect your answer to be either negative infinity or positive infinity. That was one thing we can take back from there. If you get a value, that means you might have been able to factor the numerator, right? That was a situation where you could have a hole in a graph where the value exists, you just couldn't plug that number in, okay? This piece here, though, just to encourage you, is how I knew I couldn't factor out the x plus 2. I couldn't factor this. In fact, I got irrational x-intercepts. Okay, so those would be ways to kind of help kind of encourage you this. Now, is every rational function going to look like this, y'all? No, please understand again, as I did synthetic division on this first one, it was more about let's kind of review an extreme case real quick. So that way, if it comes up, we know what to do. If not, hey, factoring by grouping is probably going to work here. This is me taking the time in class and giving you a problem that's pretty extreme. Okay, so we can go review the quotient rule for derivatives. So let's go do that. Is there any questions though with the limits before I jump forward? All right. Now, make sure you remember here, as far as the quotient rule of a derivative, it's going to be low D high minus high D low all over low squared. Okay. One thing that left me a little head scratch moment was on the second test, both with y'all in my online class. I gave you a multiple choice problem that had all the derivative rules on it. It had the quotient rule, it had the product rule, it had the chain rule. All of it was there. So when someone didn't know the quotient rule, all I could do was scratch my head because I may have not wrote it with the problem, but I gave it to you in the multiple choice problem. So make sure that you pay attention to stuff like that moving forward. Does everyone understand me with that? With that said, when I go look at this, the low trinomial here is x squared plus 4x plus 4. The derivative of the high, though, remember, we're gonna do the power rule here, right? So the first term will be 10x plus 20, and then the 19 is gone because of the zero. Minus, so low D high, minus the 5x squared plus 20x plus 19 times 2x plus 4, where the D low comes into play. Just make sure you remember it's all over low squared. Now, this is pretty ugly as far as having to clean it up, right? One thing I would encourage you here is if you didn't put it in the factored form over here, try to make sure to use the factored form for the derivative. That'll help you a little bit. What you'll find is if I go change all these, this right here was x plus 2 squared, as I showed you with the restrictions. What can we factor out of these two here? A 10. Well, what's left over when you factor out that 10? That's pretty interesting, right? Another x plus 2. Well, guess what? Guess what we could factor out of these here, at the very end? A 2, right? So here we would have times 2 times x plus 2. Now, I'm just doing some quick stuff to show that we could factor some of these, right? But what do we have in this group and in this group? X plus 2. Now, it's only one of them though, right? I factor all of them to see what happened, but what that can help you with the simplifying perspective is when we go to our next step, I'm going to put an x plus 2 out here, and then I like to use brackets. I'm getting one of those out of the way. Okay. What that's going to leave me with is 10 times the x squared plus 4x plus 4. All right. I was only able to get one of these away, and it's a little bit nicer to do 10 times this than in this form here. So that's why I'm just going to use the one that's more convenient here. But then we'll have minus 2 times that 5x squared plus 20x plus 19. It was not factorable, right? So I can't do much with it. But the brackets are important because what did I put all the way out front? X plus 2. Well, guess what? Isn't this right here just x plus 2? Oops. Sorry, y'all. Isn't this just x plus 2 squared as well? Just remember that's being squared. So that would give you 4 in the denominator. So factoring this is going to help us clean this up, which is awesome. All I have to do is distribute the 10 and a negative 2 now. Okay. So that's nice as far as that derivative is concerned. Converting this to that x plus 2 squared and then squaring it again will help us with that. So that's nice. That'll simplify out as I move forward. So what you'll find here is, to clean this up a little bit, we'll have 10x squared plus 40x plus 40 minus 10x squared minus 40x minus 38 all over x plus 2 cubed. Okay. And what's nice about that derivative, like I said, it's a little work because we had to do the quotient rule, but what's nice about the derivative? All right, what happens to the numerator here, y'all? A lot of stuff canceled out, right? And we just get 40 minus 38. So hey, guess what? That just equals 2 over x plus 2 cubed. Okay. Now, if you want to know why that works out nicely, go do polynomial long division. What you'll see is my original function is just 5 minus 1 over x plus 2 squared. So if you do the polynomial long division to get to that, you'll find that, hey, that's a little bit nicer from a graphing standpoint. You could have used transformations, but that also shows you where my derivative comes from. What's the derivative of 5? Well, it's 0, it's gone. And then remember, the derivative of something that is a rational, we can look at this as x plus 2 to the negative 2. So when we use the power rule to bring the -2 down, well, what's negative times -2? The positive 2 we found before, right? Just makes you remember it's a 3 now because we had to take 1 away from that exponent, okay? Questions or concerns, though?
Suppose x squared plus 9x plus 4 is x.
That's plus 4x. Remember, it's the same thing we started with, x squared plus 4x plus 4, 4x and 4. My handwriting is horrible, but that's what I'm writing.
Oh, not this one, the non the first one, x plus 2, I'm sorry, x squared plus 9x.
That's a 4.
Oh, that's 4.
Yeah, all of those here are the same
Yeah.
thing, just my horrible handwriting. If you think my handwriting's bad on here, you should have seen me trying to write on boards. It's even worse. Now, with that said, the second derivative is a lot nicer. Okay, so if you look at this first derivative as mentioned, this would equal 2 times x plus 2 to the -3. So the power rule is bring down the -3 and then subtract 1. Bam, there we go. So as I mentioned, seems like it's a lot to work with, but understand it's pretty straightforward once we get past that. But what is no longer in the numerator of these derivatives? Are there any variables in the numerators of the derivatives? There's no variable, right? So understand that when we get here, do we have any horizontal tangents on this function? No, right? Because there's no variable in the new. All we have is x plus 2, and I can't even put that in because it's a vertical asymptote, right? So what you'll see here is the first, second derivative don't help us much here. Okay. However, there will be some things that we can look at. So as we finish up, the one thing I would say about our function is remember we looked at the end behavior. We looked at the fact that we had a vertical asymptote. But what is the graph doing over here when I draw it? What would we say from a rate of change standpoint? It's decreasing. So that whole left side of my graph is decreasing, right? Well, that's where the x equal to -2 is going to be a critical point, right? Restrictions will end up being critical points. So when we talk about critical points here, we would still use x equal to -2. I can't actually use it because it's a restriction, but that's a critical point. Something's going on there that I need to discuss. Well, guess what? On the other side of that, what is it doing now? It's increasing, right? So understand with that, we can still use that discussion. Now, with that said, would you say these are more like positive x squared in the way that they're turning or more like a negative x squared? If we follow the pattern, don't they look more like negative x squared? So that would be like a downward direction, okay? And as mentioned, the -2 is still the focus of that. We'll call that concave down, okay? But that'll be what we jump into a little bit more Friday, and I'll try to pick some functions a little bit nicer to work with. But as mentioned, hopefully you're comfortable with the review of the quotient rule here. So that's the one thing I definitely wanted to spend the most time on, but also see where those points can help us from a graphing standpoint. Okay, so that's where we're going to continue on moving forward. Yep. Not this Friday, next Friday.